chiudere sopra, così. No.
Forse anche tocca per piccolo.
No, poi non ti si vede te, quindi bisogna...
Vabbè, non che mi dice così. Ok.
Welcome everybody to the junior seminar. Today's speaker is Alessandro Cucinotta from Oxford University, and today's talk is about perimeter minimizing sets in manifold with low volume growth.
Okay. Thank you very much for the invitation. It's very nice to be back after a few years away. And as Matteo was saying, I'm going to tell you about perimeter minimizing sets in manifolds with low volume growth. If you have, okay, so this is an analysis seminar. There's going to be some geometry. So if you have any questions, please stop me and ask. Okay, so first of all, I'm going to state the problem. Okay, so it's not, the slides are not moving. Absolutely, Karen. Sorry, I'm switching between languages. Okay, perfect. Thanks very much. Okay, so first of all, I'm going to state the problem, and then we'll give the background and the necessary definitions. So if the first slide is not clear, don't worry too much. Okay, so our starting point is this famous result that follows by work of the Georgi, Fleming, Algren, and Simons, which says that if you have a perimeter minimizing set, Euclidean space, and the dimension is less or equal than 7, then the perimeter minimizing set is actually a half space, meaning that modulo isometries, it is something of the form r to the power n-1 times 0 plus infinity. So this is a very famous, old and celebrated result. So the problem that we consider is whether something similar holds when the ambient space is not Euclidean space, but it is instead a Riemannian manifold. So the problem is the following: given a Riemannian manifold and given a perimeter minimizing set E, under what assumptions on the manifold can we deduce that the existence of the perimeter minimizing set forces an isometric splitting? So it forces the manifold to be of the form n times the real line. And it also forces the perimeter minimizing set to be a half space, meaning that it is something of the form n times 0 plus infinity. All right, so the first comment is that if the manifold is a Euclidean space, then by the theorem above, a sufficient condition is that the dimension, a sufficient condition to answer our question is that the dimension is less or equal than 7. So in analogy, we expect some smallness condition on the manifold to be the answer to our problem. Okay, so what we managed to prove with Mattia Magnabosco, is a postdoc in Oxford, is that if the manifold has no negative sectional curvature and quadratic volume growth at infinity, then existence of a perimeter minimizing set forces the isometric splitting. Okay, so I will give, okay, this is just a very brief overview. And now I will give some more background. So the plan is the following: we first give some background and we comment on some previous results. Then we state the main result. And finally, I will give a very quick sketch of the proof. Okay, any questions so far? Good. Okay, so we start from the very beginning. So a subset of Euclidean space has locally finite perimeter if the characteristic function has locally bounded variation. This is a definition, and we define the perimeter of the set as the total variation of the derivative of the characteristic function. All right, so I will give all of the background in Rn, but basically the same definitions hold in the same way in a Riemannian manifold. So let's keep this in mind for the future. But let's stick to Euclidean space for now. So our first trivial observation is that if our set is a smooth set, meaning that around every point in the boundary in a suitable neighborhood, the set is an epigraph of a smooth function. So if the set is a smooth set, then the perimeter measure, as one would expect, is the n-1 dimensional Hausdorff measure restricted to the boundary. Okay, and now we give the main definition for our problem. So the definition of a set that minimizes the perimeter in a ball. So let's look at the picture. So we consider a set of locally finite perimeter E, so the gray area in the picture, and we say that it minimizes the perimeter in a ball B, this is the dashed circle, if for every set C, such that the symmetric difference with E is well contained in the ball. So in the picture, this is the union of the gray part and the red part. So we ask that for every such set C, the perimeter of E in the ball is less or equal than the perimeter of C, and C is the competitor. Is this clear? Is the definition clear? Perfect. So these are sets that minimize the perimeter in a fixed ball. What we care about is sets that minimize the perimeter in every ball. So if we have a set of local infinite perimeter E, we say that it is globally perimeter minimizing or simply perimeter minimizing if it minimizes the perimeter in every ball over N. So this is a much stronger condition. All right. So let's have a look at some examples in Rn to get a feeling of what's going on. So, okay, the first class of examples comes from minimal surfaces. So if we have a smooth set E such that the boundary is a minimal surface, meaning that the mean curvature is 0, then it is easy to check that if we pick any point in Euclidean space, there is a sufficiently small ball, depending on the point and on the set, such that in this ball, the set E minimizes the perimeter. So this is an important, I mean, there are a lot of famous minimal surfaces, so this gives an important class of examples. An important remark is that these sets are usually not globally perimeter minimizing. So it is true that if we pick any point in the boundary of a set whose boundary is a minimal surface, so it is true that in a small ball the set will be perimeter minimizing, but it's not going to be perimeter minimizing globally. So a simple example to see this is, for example, the catenoid. So if we pick the catenoid in R3, this is a minimal surface. So if we pick the set whose boundary is the catenoid, this will have the property that in sufficiently small balls it will be perimeter minimizing. But it's not globally perimeter minimizing, because if we look at the catenoid from far away, so this is supposed to be the second picture, looking at the catenoid from far away, it more or less looks like two parallel planes, more or less. And, okay, and it's easy to check that a set whose boundary consists of two parallel planes cannot be perimeter minimizing. So minimal surfaces provide a lot of examples, but they're not exactly what we're looking for. Questions so far? No, perfect. All right, so this brings us to the examples that are actually relevant for our problem. So examples of perimeter minimizing sets in Rn. So the first trivial class of examples is given by half spaces. This is very easy to check. So something of the form Rn-1 times 0 plus infinity. But these are not very interesting examples. And then to find the first non-trivial example, we have to go in R8. So as I was mentioning in the beginning, by work of De Giorgi, Fleming, Almgren, and Simons, in Rn with n less or equal than 7, the only perimeter minimizing sets are half spaces. So we can't really find non-trivial examples there. And then the first non-trivial example of a perimeter minimizing set is the so-called Simon's cone. So we are in R8, and this is the set such that the norm of the first 4 coordinates is less than the norm of the last 4 coordinates. And this, I mean, as you can see, this is a highly non-trivial example. So this was first constructed by Simons. It's why it's called Simon's cone. But Simons didn't prove that it was perimeter minimizing. He only proved that it is minimal and stable. So this is a slightly weaker condition. And then 1 year later, Bombieri, De Giorgi, and Giusti, this was a famous paper, they managed to prove that it was actually perimeter minimizing. So this is the first non-trivial example. And this also shows that the above theorem is sharp. So it covers the full picture. Okay. Now, so this is the most celebrated example, as I was saying, but after the construction of the first perimeter minimizing sets, many more were constructed. So another key example is given by non-affine solutions of the minimal surface equations, This was done by Bombieri, De Giorgi, and Giusti in the same paper where they proved that the Simon's cone is perimeter minimizing. And so these solutions of the minimal surface equation, they provide examples. So using these graphs, if one looks at the AP graph of such a solution, one obtains a set that minimizes the perimeter. And these sets, they can be constructed from R n onwards. So we need an extra dimension to construct these perimeter minimizing graphs. And then, okay, so besides solutions of the minimal surface equation, other non-trivial perimeter minimizing sets were constructed in high dimension by many people. Here I recall Lawson, Simons, Binschalder, Cheng, and Lawlor. Yeah, these are the main names. And now the problem is completely understood. So the minimal cones, it is the minimal cones. So I'm not sure about general perimeter minimizing sets, but perimeter minimizing cones are completely classified in Euclidean space. And this is in the PhD thesis of Lawlor. All right. Am I going too fast? Probably. Yes.
The classification of minimal cones is equivalent at this point to the classification of possible singularities of minimal surfaces, right?
It's correct, yes, because if you have, if you have a singular minimal surface, whatever this means, you have, correct, if you take the blow up, then you obtain a perimeter minimizing cone, and exactly, I'm not sure if the other way around holds as well. So if you have a perimeter minimizing cone, can you always, yeah, it's trivial, it's obviously a minimum, yeah, correct, it's correct. So yes, this is also related to the problem of studying the singular set of these objects. And I mean, the fact that this result of the Georgi, Fleming, and Albin and Simons basically tells you that if you have such a perimeter minimizing set, then the subset of singular point will have codimension at least 7. So it's, yes, correct. It's related, very much related to the study of singularities. More questions? No, perfect. Okay, so now, this is the picture in Rn. This more or less explains the full picture. So now we turn our attention to Riemannian manifolds. So the first natural question is the following. So if we have a Riemannian manifold, and the dimension is less or equal than 7, so the same condition that we have in Euclidean space. If we have a perimeter minimizing set, so the existence of a perimeter minimizing set, does this imply that the manifold has to be a product and that the perimeter minimizing set has to be a half space? This is the case, obviously, in Rn. So the answer is actually very simple, and it's negative. So let's take, for example, the hyperbolic plane. So the simplest example of a manifold with constant negative curvature. So the hyperbolic plane, okay, this is just an example. So if you don't know what it is, it's not really important. So, but if we take a line in the hyperbolic plane, so an infinite length minimizing geodesic, then we can take the portion of the plane whose boundary is this line. This will be a perimeter minimizing set in the hyperbolic plane, but obviously the hyperbolic plane is not a product, and this perimeter minimizing set is not a half space. So there is a trivial example. All right, so this tells us that working with general manifolds is a bit too ambitious, and we need to work on a subclass. Now, the right subclass of manifolds to consider is the one either of manifolds with non-negative sectional curvature or the one of manifolds with non-negative Ricci curvature. And this is in view of the splitting theorem. So there is a famous result in geometry, which was proved by Topogonov for manifolds with non-negative sectional curvature and by Chigler-Gromov for manifolds with non-negative Ricci curvature, which says that if we have such a manifold, and if this manifold contains a line, then the manifold is actually a product. So very strong rigidity result. And the key assumption here is that we require either non-negative section or non-negative Ricci curvature. So this key result, together with this very simple example, tells us that the right class to study our problem is the one of positive curvature in some sense. Okay, now, so if you don't know what sectional curvature or Ricci curvature is, don't worry. Now, okay, I'm just going to give some previous results on this topic, so there will be a lot of curvature assumptions. But then once we look at the main theorem, I will isolate which properties that follow from curvature assumptions we're going to use. So it's not really, I mean, even if you don't know what it is, it's not really important. Right, any questions so far? No, perfect. Okay, so let's have a look at previous literature in the setting of Riemannian manifolds. So an important result that we will also consider later, so I highlighted it, is by Anderson in the 90s. This is an old result, which says that if we have a manifold with non-negative Ricci curvature, sectional curvature bounded from above and from below, so this is a very strong assumption, and at most cubic volume growth at infinity, so volume growth, so the volume of the ball of radius R is at most r to the power 3 for r very large. So under these assumptions, if there exists a perimeter minimizing set in the manifold, then the universal cover of the manifold splits off a line. So the universal cover is a product of the type something times r. So this goes in the direction that we were considering before. There are a lot of assumptions, and the splitting is not on the manifold, but it is on the universal cover. Okay, so this is also important. So a previous theorem of the same type was done by Anderson and Rodriguez for 3 manifolds. So this is a key result that we will look at later. Okay, besides this one, there are many other results. I decided to isolate 2 of them. So Carlotto, Chodos, and Eichmar, very recently, they considered 3 manifolds that are asymptotically Euclidean. So they look like R3 out of a compact set, more or less. And they also assume non-negative scalar curvature, and then they show that if there exists a perimeter minimizing set, then the manifold is actually R3. So there is a lot of splitting. And then with Francesco Fiorani, who is also a PhD student in Oxford, we showed that if we have a 4 manifold with vanishing Ricci curvature and Euclidean volume growth, then if there exists a perimeter minimizing set, then this manifold has to be R4. So even in this case, there is a lot of additional splitting with respect to, in addition to what we ask. Okay, so these are only some results on this problem. But in general, there are many more existence and non-existence results for minimal surfaces and for perimeter minimizing sets. And some of these are very famous and are due to Yao, Fischer-Kobrishcher, Nabonnand, Jost, and many others. Okay, so this is more or less the historical account. Any questions on this part? No?
How sharp are these results? Do they have like existence of manifolds which are, for instance, do you have existence of 4 manifolds which are not Ricci flat, for which you have another perimeter minimizing set?
Yes. Yes. So yes, there are counterexamples. The main counterexample for us, I will mention it later. But let me anticipate what it is. So Ding, Jost, and Lee, I think, they constructed a 4 manifold with strictly positive sectional curvature, which contains a perimeter minimizing set. So if the sectional curvature is strictly positive, you cannot split the line. So this shows that the problem fails in general if you don't have a lot of assumptions. And also, yes, exactly. So this is the main counterexample to have in mind. But there are a lot of other counterexamples that come from work of Morgan. This is earlier, but these are in Alexandrov spaces. So, but yes. So the answer is yes. The assumptions are needed. Like if you remove the assumptions, things will not work. Okay, so this takes us to the next question, which is more or less, in a way, it's what you were asking. So, what if? So, okay, so this is also important. So, in all these results, there is a bound from above and from below on the curvature. So, in Anderson's result, sectional curvature bounded uniformly. In Carlotto, Chodos, Eichmar, assuming that the manifold is like R3 asymptotically, is also implies that the curvature has to be asymptotically flat from above and from below. And okay, with Francesco, we have this very strong assumption of flat Ricci curvature. So all these results, they have curvature assumptions from above and from below. So the natural question, also in view of the splitting theorem, which only requires the negative Ricci curvature, is can we say something having only a lower curvature bound? And this is okay, and this is where our main result comes into place. So let me read it first, and then we'll make some comments. So what we managed to prove is the following: if we have a manifold with no negative sectional curvature and quadratic volume growth at infinity, here it is enough to have a limit. So it is enough to have a sequence of scales such that the volume of the ball of radius r over r squared stays bounded. So okay, this is weaker than obviously having the ring suit. And okay, so under these 2 assumptions, if there exists a perimeter minimizing set, then in the manifold, is a product, and the perimeter minimizing set is a half space. Let me make a few comments. So the first comment is the example that I was mentioning earlier. So okay, so there are 2 key assumptions here: the negative sectional curvature and the volume assumption. if you remove the curvature assumption, it's very easy to see that things fail, that the result is false. Simply take S1 times R, take S1 times R plus as the perimeter minimizing set, and then perturb the metric far away from the boundary. And this will not have no negative sectional curvature, and the theorem fails. So the non-trivial fact is that if we remove the volume assumption, also in that case, the theorem fails. And as I was saying, this is by Dingios and Lin, because this is what I already said. So there exists a four manifold, which is not a product, and which contains a perimeter minimizing set. Okay. Now the second observation is that even though both assumptions are necessary, the theorem is not sharp, probably, because if you remember, so in Anderson's result, so let's go back a bit. So in this result, which is kind of similar to ours, you have cubic volume growth at infinity. And in the counterexample, so in this counterexample by Dingios and Lin, you have quartic volume growth at infinity. So we know that for quartic volume growth at infinity, the theorem fails, but most likely it will hold for cubic volume growth. So this is something that we didn't manage to do. Questions on this or the result? Yes.
They said E a priori is non-smooth.
It's not smooth. Yeah, this is a good question. So the set E is non-smooth, yes, because we have no restriction on the depth. So okay, if the dimension is less or equal than 7, then regularity theory gives you all the smoothness you want. So if the dimension is arbitrary, you can have obviously non-smooth sets, but the truth, so this is maybe quite counterintuitive, the truth is that this condition also gives you the smoothness of the set. It's very counterintuitive because this is a global condition. So you expect, I mean, regularity is a local property. So you would expect.
Yeah, posteriority.
No, exactly. No, but even so even if you're not able to prove this, it's easy to see that this gives you regularity. I can tell you very quickly why. Let me see how much. Okay, we have a lot of time, so let me tell you. So okay, so suppose that you have a perimeter minimizing set in a manifold. Okay, perimeter minimizing. And okay, and you have and suppose that there is a singular set. So there is a subset of the boundary which is a singular point. Now, outside of the singular set, I'm gonna be quick, so I'm not gonna give you the full proof. But outside of the singular set, your perimeter minimizing, the boundary of the perimeter minimizing set is a stable Euler surface. Yeah, this is easy to see. And so you have the second variation. So the second variation formula holds, which means the following, which means that if you have on the boundary the following holds, let me write it. Sorry. So what? Is this fine? Is this fine?
Yeah. It's difficult to switch.
Posso tiltare un po' il computer? Ok, perfetto. Can you, from home, can you see? I think so.
Yes, thank you.
Perfect. Okay, so let me, so you have the second variation formula. Let me just write it and then I'll say what it means. Okay, and the formula holds outside of the single set, as we were saying, supported in the boundary minus the single set. Okay, so you have the second variation formula. So outside of the single set, you have the second variation formula, which tells you that if you take a function which is defined on the boundary, but only in the smooth part, and then it's 0 on the singular part, then the integral of phi squared times the second fundamental form of your set times the Ricci curvature in the normal direction, which is defined because in the end we only care about the smooth. I mean, we only care about the smooth part, obviously. Okay, then this will be less or equal than the energy of the function. Okay. Now the point is, by regularity theory, we know that the singular set is very small. So if this is the same principle, so if you have a function bounded variation defined on an open set, such that the complement of this open set has 0 one capacity or 0 n-1 measure. So basically the single points are small enough so that we can ignore them. So we can have this formula for every compactly supported function also across a single set. This is, as I said, due to regularity theory. Okay, and now once we have this, the point is, if we can fix, sorry, maybe this is longer than, maybe you didn't want to know the full story, but it's, so the point is, if you fix a ball in the boundary, now you take all the functions phi that are 1 on this ball, and you minimize this quantity among all those functions. Now this volume growth assumption will tell you that you can get this to be 0 when you take the mean. And the non-negative Ricci curvature assumption, we have a negative section, but non-negative Ricci is the same, tells you that this quantity is positive. So basically, on every ball, you can get this integral to be 0. And so okay, I will skip some steps, but then this gives you that the fundamental form is 0 everywhere. So your set is totally geodesic outside of the single set. And now you can run Federer's dimension reduction argument. Okay, there are some technicalities, but basically you reduce the problem of adding singularities to a problem in Euclidean space by taking blow-ups. And you see all the pathological cases are ruled out by this fact.
There is sufficient Ricci curvature.
Yes, so Ricci curvature is sufficient, and also you don't need that. Okay, the two assumptions that you need is this one. The two assumption that you need is this one. So this is a weaker, so this is implied by our volume growth assumption, but this is the two condition that you need. The reason why you need this condition is that this condition of the volume growth of your manifold tells you that when you restrict yourself to the perimeter minimizing set, this is going to be parabolic. If you know what it is, good. Otherwise, you can believe it, but this is no problem. This is how it works. Okay. Okay, so yes, in particular, the set is also smooth. This is an important comment. All right, let's keep going. So, okay, so now we sketch the proof. Before sketching the proof of the result in the Riemannian case, let's have a look at the proof of the main result by work of the Georgi, Fleming, Dahlgren, and Simons, because our proof kind of follows the same lines. So we have a perimeter minimizing set in Rn, and we want to show that it is a half space. There are 3 steps. So the first step, we take rescalings of our perimeter minimizing set, which means we take E over Ri for some sequence Ri going to plus infinity. Now, okay, these rescaled sets, they are all perimeter minimizers. This is easy to check. And by a powerful result, the monotonicity formula. So, okay, so they converge when Ri goes to plus infinity, they converge to a limiting set that we call E infinity by standard compactness arguments. And then by a powerful result, the monotonicity formula, we have that the limiting set is a cone. So by doing this procedure, we gain some extra regularity. Okay. Now the key step is that by a result of Simons, essentially, if you are in Rn and n is less or equal than 7, then all minimal cones have to be half spaces. So this limiting set infinity has to be a half space. This is where the dimension really enters into play. But now, if we look at the monotonicity formula once again, we realize that it also gives the rigidity, meaning that not only the blow down of our perimeter minimizing set is a cone, but if it is a half space, then also the initial set has to be a half space. So this is a very okay. So this is the strategy in the Euclidean case, very sketchy, but these are the main steps. And what we would like to do is to basically do the same in our setting of Riemannian manifolds. The issue, obviously, is that in Euclidean space, we can take rescalings of sets, and we can do this because the space is homogeneous under rescalings or invariant under rescalings. In Riemannian manifolds, this is not possible, so we need a lot more machinery, and there are some subtle complications. Questions on this? No, perfect. All right. So before having a look at the proof in the Riemannian case, let me give you the machinery that we will use. This is basically all the background on curvature that we need. So if you believe these results, then you can forget about sectional curvature. Okay, so let's pick a manifold with a negative sectional curvature. This is important. If we have a sequence of scales going to plus infinity, if we consider the same manifold where the metric has been rescaled, so we are compressing the metric, then up to passing to a subsequence, these manifolds, they will converge in a suitable sense, in a sense which is suitable to metric spaces, to a limiting metric space, to a pointing metric space. Pointed means that we are highlighting a specific point. So if you don't know what pointed Gromov-Hausdorff convergence is, it doesn't matter. It's just a notion of convergence for metric spaces, which is the analog of Hausdorff convergence of sets in Euclidean space. But it's not really important. Okay, so by a powerful result of Gromov, we can take these rescalings of manifolds and they will converge to something in the limit. The space, okay, such a space is called a tangent cone at infinity of our manifold. Simple example, just to get a feeling. If our manifold is of the form R times something compact, when we rescale the metric, when we zoom out, the vertical line stays the same, and the compact slice gets shrunk to a point. So the tangent cone at infinity of a cylinder is going to be a line, as one would expect. Questions on this? No. Perfect. So a few comments. So all that I'm going to say now holds only for the tangent cone at infinity of manifolds with non-negative sectional curvature. So this assumption is very important. So these tangent cones at infinity, they have a lot of properties. And these properties, they were studied by Gromov and Kasue. They were mostly stated by Gromov and then proved by Kasue. Okay, the main properties that we need are the following. So the tangent cone at infinity of a manifold with a negative sectional curvature is unique. So it doesn't depend on the sequence of rescalings that we pick. The second comment is that the tangent cone at infinity is actually a metric cone. So it is a metric space which has the structure of a cone. And in particular, it's going to be a metric space that's invariant under rescalings of the metric. And then the final important point is that if we are able to say that the tangent cone at infinity splits isometrically as a product of some metric space times R, then also the initial manifold will have this structure. So also the initial manifold will be of the form n times R. As you can see, I mean, if we have in mind the proof of the main result by the Georgian and the others in Euclidean space, it's not hard to see how this machinery can sort of replace their main tools. Important question. So all these properties, they hold for tangent cones of manifolds, tangent cones at infinity of manifolds with non-negative sectional curvature. But tangent cones at infinity can also be defined if you have the weaker assumption of non-negative Ricci curvature. But then all these properties fail. In the counterexamples, they can all be found in the paper by Chigger and Holding. So the non-uniqueness was also done by Perelman before. Questions? No, perfect. Okay, so now we're ready to sketch the proof. Okay, let me read the statement again. So manifold with non-negative sectional curvature, quadratic volume growth at infinity with limit. If there is a perimeter minimizing set, then the manifold splits and the perimeter minimizing set itself is a half space. The three main steps, they follow the strategy, as I said, of the Euclidean case. So the first step, we take a tangent cone at infinity of our manifold, and we consider a set E infinity, which is naturally induced by E, so by our initial set. Then the key step, this is the hard part. So we show that in the setting of the tangent cone at infinity, we have the result that we are hoping for. So we show that the tangent cone at infinity splits as a product, and that the set E infinity is a half space. And then finally, we go back to the initial manifold. So from the result on the tangent cone, we deduce the result on the initial manifold. Okay, so step one is basically done by known results. So as I was saying earlier, existence of the tangent cone at infinity comes from Gromov. Now on the tangent cone at infinity, not only we have the structure of a metric space, but we can also induce a measure in a natural way from the volume measure of the manifold. And so we end up, okay, so by doing this, we end up on a metric measure space. So on a metric space equipped with a measure. Now on these spaces, there is a rich theory on of sets of finite perimeter and perimeter minimizing sets. This is due to Ambrosio, Miranda, and then their students mostly. And in particular, by a recent result of Ambrosio, Brouet, and Semola, if we start from the set E in our manifold, then this induces a perimeter minimizing set in the tangent cone at infinity, perimeter minimizing with respect to the metric measure structure, and perimeter minimizing in the sense of Ambrosio and collaborators on metric measure spaces. All right, and for those of you that know the theory of RCD spaces, this tangent cone at infinity will, I mean, it is a RCD space. These were introduced by Gigi and others, and this will be a key fact that we're going to use later on. Any questions on this? No? Perfect. Okay, so this is step one. As you can see, we did almost nothing. It was already there. Now, step two. This is the most challenging part for us. So now we have the tangent cone at infinity X and the perimeter minimizing set infinity. We need to show. So we need to show the statement with respect to these two objects. So what did we gain? Because this is exactly the statement that we were trying to prove in the manifold. So what did we gain by taking the tangent cone at infinity? What we gained is that the tangent cone at infinity has to be a cone, and so in particular there are only very few options that we need to consider. Okay, so we know that the tangent cone at infinity X is a cone by Gromov and Caswell. Now, by a result of Sormani, I mean, this is not a direct consequence, but it follows more or less with standard tricks. By this result, we can say that this tangent cone at infinity will have Hausdorff dimension at most 2. So there are very few options. So X has to be either R plus modulo isometries, the cone over a circle of radius R, or the cone over an interval of length less than pi, for reasons that I'm not going to explain. Okay, so there are only very few options that we need to consider. Now, if X is the real line or it is half of a real line, this is trivial. I mean, if it is the real line, then we don't have to prove anything. And if it is half the real line, it's easy to see that there cannot be perimeter minimizing sets, so it cannot be half the real line. So the first non-trivial case is the case of a cone over a circle. So with Mattia, we managed to prove the following. We managed to prove that if the cone over a circle arises as tangent cone of a manifold, or more generally, if it is a RCD zero-end space, then the measure has to be a multiple of the two-dimensional Hausdorff measure. So the measure has a very precise structure. And this is essentially a consequence of the splitting theorem by Gigi, even though it's not, I mean, it's not a direct consequence. There is some easy work to do. All right, so in the case when X is metrically a cone over a circle, then we know that we have all the information also on the measure, and then we can apply an old result by Morgan that says that if you have a perimeter minimizing set with respect to this structure, then it means that the radius of the circle is actually 1, and so the cone is actually R2. So you have all the splitting that you want. So this case is also somewhat simple. Now, the truly hard case is the case when X is a cone over an interval. Now, you can't see it, but under the Zoom windows, it says cone over an interval. Okay, so this is the challenging case. So the first observation is that in this case, in general, the measure is not a multiple of the Hausdorff measure. Okay, so we need to do something else. Nevertheless, it is sufficient to prove that the measure is less or equal than some multiple of the Hausdorff measure. And then we can apply some standard machinery to conclude as we did before. Okay, so now I'm not gonna, so there are 3 steps to prove this. I'm gonna be quite vague. I'm just gonna mention the main tools. So step 1, let's look at the initial manifold M. So if the boundary of the perimeter minimizing set is compact, then everything follows by a standard result of Caswell. So we can rule out this case. If the boundary of the perimeter minimizing set is non-compact, then we can show that in the initial manifold, at infinity, not only the volume is at most quadratic, but it is also at least quadratic. So the volume measure at infinity has a very precise behavior. Okay, this is the first step. And this essentially follows, I'm not going to be too specific, so this follows by a known result of Yau that tells you that a non-compact manifold with non-negative Ricci curvature has at least a linear volume growth at infinity. So by using this result, we're able to deduce that our manifold has at least quadratic volume growth. Okay, so this is the first step. Now the second step is that by step 1, by step one, the measure in our tangent cone at infinity must have at most quadratic volume growth at infinity. So this regularity somehow transfers to the limiting measure on tangent cone at infinity. And now, by using known regularity properties of measures arising in this way, this is the needle decomposition by Cavalletti and Mondino, we're able to prove that this measure has the control that we want around the boundary of the limiting perimeter minimizing set. This is very vague, but yes. And then step three, using a recent result of Mondino and Segola, we are able to globalize and to translate this bound near the boundary of the perimeter minimizing set into a global bound. And this is essentially due to the fact that if you take the distance function from a perimeter minimizing set in a metric measure space, in an RCD zero-end space actually, then this is going to be super harmonic. Okay. Okay, and now as I said before, so this is the vague strategy. Once we have that the measure is less or equal than a constant times the two-dimensional of measure, then we can use simple machinery to deduce that X is actually a product and that E infinity is also a product. Okay, so now we are left with the last step. So now we have the regularity on the tangent cone at infinity. We need to deduce the regularity on the manifold. So well, first of all, by a result that I was recalling earlier, since the tangent cone at infinity is a product, then also the manifold is a product. This is already done. And then since the set E infinity is a half space in the tangent cone, adapting an argument by Antonelli, Bureau, Gagnol, and Pozzetta, we deduce, this is very simple, we basically copy their argument. We deduce that also the initial set is a half space. And this concludes the proof. Any questions? This was very vague, but maybe just to give a flavor of the tools. Why are you laughing? No? Okay, fine. Okay, so this is it. Now there are some final open questions, but now the question is it possible to improve our result? So the first question is, if you have a manifold with non-negative Ricci curvature instead of sectional, and volume growth, cubic volume growth, so like R3 instead of R2, can you deduce that if there exists a perimeter minimizing set, then you have the splitting and the perimeter minimizing set is a half space? This is, okay, as we were saying, so this is motivated by the result of Anderson. So if you remember, let's go back. There was a related result of Anderson, which only assumed, there was this result of Anderson, which assumed cubic volume growth and negative Ricci curvature. So the question is, are these assumptions sufficient? Okay, and also, okay, so this is motivated by Anderson's result, and also by the fact that we know that if this is quartic volume growth, then the result fails. So, okay, and then the final question is, this will sound much more specific. So if you have a manifold of dimension 5 with non-negative sectional curvature and scalar curvature greater than 1, if there exists a perimeter minimizing set, do you have the splitting and the splitting of the perimeter minimizing set? So this is motivated. So first of all, by a famous result of Petruni, these manifolds, they will have cubic volume growth at infinity. So if one manages to prove the first conjecture, then this one follows as well. But the reason why we stated this version of this problem is that it is the global version of a recent conjecture by Chodosh, and Stryker. But it's not, I mean, it's unrelated to that conjecture. I'm not going to say much more on it. Let me just say that initially, the reason why we considered this problem was that we were trying to prove the result under this assumption, adding 4 instead of 5. So this is and then okay, our result implies this with 4 instead of 5. So this is initially why we were looking at this, and so this is a natural generalization. All right. This is it. Thank you. Thank you for your attention.
The first is Where did you use the bound on the sectional curvature precisely in the proof? Because most of the results we follow just
Correct.
on
Correct.
bound on the curvature.
There are actually, no, we use it in several points. So, so where is it? Sorry, okay. So we use it in several points. So, okay, all of these Ricci curvature is enough. All of these also Ricci curvature is enough. Actually, no. So this already fails. So okay, you can show that so if you have non-negative Ricci curvature, you can show that the tangent going to infinity okay, you can show that tangent going to infinity will have essential dimension at most 2. So you don't get the Hausdorff dimension, you get the essential dimension. But this is not per se a problem. But then you don't know that it's a cone. So you don't, so okay, if the essential dimension is 1 by Kitambepu and standard factor, then okay, you only have these cases. If the essential dimension is more than 1, then you can't reduce yourself to these cases. There is the famous example of the blow down of a manifold with negative Ricci curvature, which is metrically a worked product. So not a cone. Okay, so this is the first issue. But then there are several other issues. Let me see. So okay, so the main 2 issues are the fact that you don't have the structure of the blowdown, which is what I was saying, and that the splitting of the blowdown does not tell you that the initial manifold splits. And this is a major issue because obviously you want to prove something on the manifold. So yeah, so these are the two main problems. And there is also, sorry, there is also another last problem. So in this first step, this is maybe a bit subtle, but in this first step, what we do is the following. So we show that the boundary of the perimeter minimizing set, basically due to this argument, will be totally geodesic. Now, if you have a manifold with a negative sectional curvature and a totally geodesic submanifold, then also this manifold will have no negative sectional curvature by Gauss equations. But if you have a manifold with no negative Ricci curvature, then it is not true that a totally geodesic submanifold will have non-negative Ricci curvature. So okay, so you either impose some, you can ask for n-2 non-negative Ricci curvature, so there are these intermediate conditions. But so yeah, so you have all sorts of issues at all steps, basically.
And the other thing I wanted to ask is, did you use like a lot the regularity on the original manifold, the smoothness of the original manifold?
Good question. We did, mostly for the following reason. Okay, so if you have a manifold, okay, so if you have a manifold with quadratic volume growth at infinity, let's say with the lim sup instead of the lim, so strong assumption. So it is not entirely clear to me if it directly follows that you have blow down of dimension 2. So is this clear what I'm saying? Okay, so in our point, so the point is that there is this result by Sormani that tells you that if you have linear volume growth in infinity, then you have blow down which has dimension 1. So the reason, so how we use this is that we have our manifold. Sorry. Let's try like this. So okay, so we have our manifold M, and we have the perimeter minimizing set E, and then there is something else. So once we have proved that this is totally geodesic, then we consider the metric space. So I lied, it's not there are some extra steps. So we consider the metric space given by gluing E along its boundary, which is smooth and totally geodesic, with the boundary times R plus. So we consider this manifold, and now we are gluing a copy of times R plus. Okay, so this is so under our assumptions, this is still going to be an Alexandrov space by parallel, basically, but we are using critically that this is a smooth, that the boundary of it is smooth and has vanishing second fundamental form. So why do we need to do this? Because we know that the boundary of E will have linear volume growth at infinity, so we'll have one-dimensional blow down. And so by doing this, we are able to say that this glued object will have two-dimensional blow down. And then constancy of dimension for Alexandrov spaces, it means that also the addition manifold have two-dimensional blow down. So if you don't have the regularity, you can't really do the gluing. So maybe you have to show that an Alexandro space with quadratic volume growth has glue down dimension 2. So Lichak says that this is true. It's probably true, but I never really sat down to do it. So yeah, so we do use the regularity, actually.
There is a question from home.
Yes? How does it work? Vediamo. Ah, thank you for the talk. Prego. You're welcome.
Any other questions?
Thank you. Perfetto, adesso posso dire... Ah, no, è ancora registrato.
Sei termine.